Hello, welcome back to EEforEveryone, part 15 of the Plant Life project. Today we're going to attempt to add some feedback to determine whether the fan is actually spinning. That way, our microcontroller will be able to turn off the LEDs if they're not being cooled. If my research is correct, this will be an open collector output, which we can connect, which the fan will connect to ground twice per revolution. If this is truly the case, then a pin configured as an input with a pull-up resistor would be able to be directly connected to this pin, and that would give us 2 pulses per second, or 2 pulses per revolution. I don't have the specs for this fan on hand, but I think we'll be able to see whether or not the numbers are reasonable. Number of revolutions per minute. If this is truly open collector, that means the 12 volt applied voltage won't ever be delivered. It'll just be pulling that signal down to ground, so we wouldn't even need any input protection circuitry for the microcontroller. That sounds just elegant enough, like an engineer somewhere might have came up with it. And you know, that would work out great for this design, because we'll only need to add 1 wire, then configure that input correctly on the microcontroller. So, we've got the oscilloscope hooked up. We're going to make sure that this signal's behaving the way that we expect it to, and then once that's done, we'll implement what we found as a schematic change, a layout change, and then write some software after we rework one to go ahead and apply the change. With all of this complete, our software will be able to determine whether or not the fan is spinning, and then disable the LEDs if the LED is not spinning. Let's begin. With the fan turned off, it looks like that signal is pulled to ground. What happens if we turn the fan on? We're hooked up to the wrong signal. Now, let's give this a shot. Let's flip the fan on. Hey! Oh, look at that. That looks like PWM. And it looks like it's come from an open collector output. Oh, that's great. Oh, you can't see the... Oh, okay. I just switched scenes. Now you can see. So here you can see the square wave on the left side of the screen, channel 1, maximum of 3 volts, where I believe that because our pull-up's a little bit too weak, and the frequency as measured by the oscilloscope is 137.8 hertz. So that's cycles per second. So if we take that and convert it to revolutions per minute, or well, pulses per minute, that'd be 137 times 60. 8,000 pulses per minute. It sounds a little fast for a fan, but I believe that that was 4,000 revolutions per minute. Seems to check out. You know, I've got a box for one of these CPU coolers over there. Let me grab it and I'll check what it's rated for. I've got the box for the cooler now, and you would not believe this is rated for 3,700 RPM plus or minus 10%. 4,000. There you go. So 4,000 RPM, measuring 4,000 RPM. Let's get a higher value pull-up resistor and see if we can get that to go up to proper 5 volt logic. Got our new resistor. Hooking that up to the signal that we're measuring. And then the 5 volts. We'll run that. Okay, we're seeing 5 volts now. Turn that on. Oh, beautiful square wave. And in fact, you can watch the fan accelerate. So I believe this signal is doing exactly what we think the signal is doing. This should be safe to connect directly to the microcontroller. Awesome. Let's grab a wire from the bin, tack that onto an unused pin, and let's start measuring the speed this fan is spinning. The pull-up resistor is integrated in the microcontroller. So literally all we need is the wire. That is awesome news. Couldn't be better, in fact. This will be an easy change to implement in both the layout and right now when we're trying to make it work. The key thing is that we need to find where we want to actually connect that wire. I don't know what our sample rate would be. I wouldn't really want that to be an interrupt, though it could be. A general purpose I/O should be sufficient, because as long as these two frequencies aren't perfectly in sync, which they won't be in lockstep, it's not a phase lock loop, they'll be drifting with respect to each other. So if we're pulling at a frequency, and this is changing at a frequency, eventually we will be pulling it when it is low. So we just pull it and make sure that 1 out of every 100 samples, the value has changed. And then that'll be fan spinning equals 1. Any unused I/O pin will work just fine. And we have 2 unused pins on the plant light, so we can go ahead and route on the board. We can tack a wire from the signal to one of those unused pins. I know that one of these pins is connected to 24 volts. Okay, let's get the multimeter. Change this to continuity mode. Yeah, this is awesome. I love it when it works out. I wish I would have thought of this when I was laying out the next rev of this board, because this is just awesome. This is great. Okay, so this pin is hooked up directly to 24 volts. The next 2 pins have no continuity either way. We just need to route pin 3 of this connector over to this pin right here. Then that'll give us a pad off the switch that we can use. So we'll have 1 wire tacked from there to the microcontroller and 1 on the power board. Turn on the ventilation fan. Turn on the soldering iron. Let's do this. This is the mounting plate where the power board screws onto. So he's got the holes in place for all the LEDs, and more importantly, the board supports, which we need to avoid when adding this tack wire. Close to the edge of the board, we can route along the serial number label and then come up near the front. Or, well, same spot on the opposite side of the board. Scrap bin acquired. This one looks good, nice and thin. Wire stripper acquired. Just going to prepare this wire by tinning it and removing that old one. Awesome. Since this is stranded wire, we'll probably have to use a little bit more tape or something to hold it in the correct place, but it'll also be easier to move around if it turns out we need to move it. Okay, looks like that should be enough wire. We have the wire soldered in place. So I'll grab some Kapton tape and tape this down to the board. Unfortunately, it wasn't in the last place I looked, but I have some regular tape. This isn't the ideal kind of tape I'd like to be using. Unfortunately, I can't get something delivered in 2 minutes. and we'll just have to wait to order some. This will secure the wire for now, and before I go ahead and make this change on the other lamps, I'll make sure to buy the right tape. Okay, so the wire's been secured. Let's make sure that wire doesn't interfere with the housing. Oh, no, no, no. Oh, the wire is hitting one of the supports, so it didn't get out quite far enough. Oh, it's really close too. Ah, that's a shame. Okay, so I know where to route it. We'll use this piece of wire for the control board. So in order to ensure that we don't have any issues, we need to route around this mounting point, come back around, and then solder the wire on over there. So then we want to go to the second. If we go ahead and try to put this in the enclosure. Oh, look at that. Fits like a dream. The layout is open. So I notice there's a net power off. And I don't believe that net is actually going anywhere. Should be pin 2 of the package. Let's highlight this net. Oh, that's already going back to a pin. Oh, we wouldn't even need a bodge wire. Now that is perfect. Remember in the previous episode when I mentioned that there was an unused pin on there was the power latching circuitry? Well, turns out the control board has that signal still routed since it was designed for the version of the board that has that circuitry. All we have to do is move this wire over one position, or we have to move that over 2 positions to go from the button over to where it's adjacent to the 5-volt net. So it'll be button, button, no connect, and then this signal routed to that pin of the microcontroller. Perfect. I think there's enough slack that we can get this to where it needs to go. So now we're going to the 4th pin of this connector. Again, I'm going to connect the wire in between the no connect and the pin we actually want to connect to, so that if the wire were to break free and short against an adjacent pin, it wouldn't damage the microcontroller. The power off pin, pin D4, will actually be fan spin sense. And that's the only rework we need. We're done. The change has been implemented, and we need to route one trace from J7 over to that connector. And so we'll consider that J7 is the master fan, the LED cooling fan, and we'll call the other one the auxiliary fan, which doesn't need feedback. So we need to go over to the software, set that pin to a digital input with the Pullup Resistor enabled, and we should be able to determine whether or not the fan is spinning. Great. All we need to do is go into the button class. We're going to add a new function called bool get fan, and this will return a 0 if not spinning and a 1 when spinning. And to do this, we're going to need an array of Boolean numbers, bool fan spinning, and we'll have 10 samples. Hopefully 10 samples is enough. Num fan samples, and we'll set that to 10. That way we can reference that same variable, so if we need to tweak up the number of samples we have to actually get a reliable result. So basically we're going to take that number of samples, make sure that at least one of them is high and at least one of them is low. And we're just hoping that with how the two will interact, we will get some samples of both and it'll just work out. We'll call that fan spinning buff for buffer. We need to define that pin. Pop open the schematic program. Port D4 is, Arduino pin D4. It looks like there is a pin change interrupt. It would be awesome to use this pin change interrupt. However, I don't want to interrupt the processor that often to service this. Then again, if we use the pin change interrupt, we could actually count the number of pulses and the amount of time passing and determine the speed with which the fan was spinning. Spinning versus not spinning should be sufficient for us. We'll give this a shot, and if it works, great. The button class will be monitoring that pin and has a function that will return a 1 if it believes the fan is spinning and a 0 if it does not believe the fan is spinning. Now we need to change the UI class to actually respond to that input in the run LEDs function. Alright, so I've finished the code. It compiles. Let's put this on the lamp and see if it works. Clearing off the bench a little. Welcome back. I have to admit, I checked the code for bugs before I came back to the bench. I made sure that the code will successfully turn off the lights if the fan is not detected. And I verified with the status menu on the screen that, in fact, it did. I'll point this at the camera so hopefully you can get a good look. Again, this is the board that we reworked. Added that wire with the sense line. And hopefully nothing will break. So what happens is, if all is well, the lamp will begin to turn on. And I'll just hold this heatsink on there. As it fades up, when the threshold that the fan should turn on is exceeded, the fan will begin to spin. The button class should begin to see the pulses from this open collector output turning on. The buffer should be large enough that because it's sampling at a different rate than it's oscillating, it'll always detect at least one sample out of the 20 that has a different state. At least that's the theory. Maybe it needs to be 50 or 100 samples, but I know that if the fan is not spinning, every single sample will have the same state. And once we are in the time where all of the LEDs are at full power, have reached their set point, the fan should remain spinning and the LEDs should stay on for as long as that fan is detected. Let me unplug the fan and see if it responds appropriately. So now the button class should be detecting that it's no longer getting the pulses, and both the button class and the LED driver class is running its rolling average. When both of those moving averages detect that the fan has stopped spinning, it turns off the lamp. If we plug the fan back in, both classes should detect that the fan is returned. Oh, but they won't. The classes won't detect that the fan has returned because the fan isn't spinning. However, if we were to give this a bit of a jump start, there's no power. It'll never see that. So perhaps we should have a timeout where it'll attempt to turn the fan back on in case there was a little bit of noise. That seems like a good addition to our program. Here we go again. The light is powering on. The code has been updated. It's got some code where periodically it'll give the LEDs a burst of power which will tell the fan to turn on. Though I didn't really do any timing analysis on the duty cycle. So I have a counter basically, and if that value, so there's 100 consecutive samples where the LED driver is told that the fan is not spinning, it will turn off the LEDs in the fan and continue counting until it gets up to 2000, at which point it will reset the value to 50 and it will continue. As it's counting from 50 to 100, the fan will be given a chance to send some pulses and hopefully latch the lamp back on. Though I don't know how quickly it counts, and I don't know how long the fan needs to spin up. But hopefully we'll get at least a couple of revolutions before that time is exceeded. Looks like we're in normal operation. Let's unplug the fan. Now the code should have detected. Whoa, that was fast. So that counter takes a while, because before that was set to 500, and it took it that much longer to detect the fan had stopped spinning. So I need to wait for it to get to 2000, and we should see the light flash for a little while. I'm watching very carefully because I don't want to miss it. This takes a long time. Oh! Hey, look at that. So the light flashed for just a moment after being off for quite a long time. The idea is this heatsink can passively dissipate some heat. So as long as there isn't too much power being asked of the lamp, the lamp's not requesting it to dissipate 30 watts continuously, the fan doesn't need to spin. That pulse was maybe 2 or 3 seconds long, so if the fan was truly spinning in that 1 or 2 seconds and it had recovered, we would expect the lamp to allow this to turn back on. We just need to wait for that 2000 counter to pull the signal 1900 times and try to turn on the LEDs again. If all went well, the light should tick on, the fan should start spinning, the microcontroller should see some pulses, and it'll all come back to life. Here's hoping. If you think that preventing our LEDs from melting the enclosure is cool, and this video is great, let me know by hitting the like button on this video, subscribing to the channel, and leaving a comment letting us know what you enjoy. Most of all, I hope that you learned something great today, and I hope to see you again soon. Bye!